So I will speak about turbulence, turbulence which is a kind of two-dimensional turbulence, and basically to explain the self-organization of the larger scale of the flow in a geophysical turbulence. And there will be some examples of abrupt transition and phase transition. So I will be a bit fast with this first few slides. So one example, for instance, is the way the turbulence self-organize on Jupiter planet, so on Jupiter troposphere. And so the main feature is that there is a self-organization on the large scale. You can see here these bands. So these bands corresponds to the main flow flowing mainly eastwards or westwards, as you can see on this plot. What is plotted here is the velocity as a function of the latitude. And so there is also this big feature here, the great red spot, and some other features. So it is a genuine turbulent flow, but the phenomena is really different from the one that has been discussed by David Ruel this morning. Here the phenomena is a flux of energy towards the large scale. This flux of energy is no more local in the scale space, in Fourier space, as soon as you have this large scale feature. So it's not a local flux of energy. So the phenomena is really there in the physical space. And what we try to do is to predict the velocity profile. So there are many examples in nature of turbulent flow that have different attractors. So this is an example which is in the MHD, magnetohydrodynamics. So this is a turbulent dynamo that has been obtained experimentally by some colleagues in Paris and in Lyon. And you can see here the magnetic field as a function of time, and the magnetic field changes randomly its polarity from one attractor to the other. Maybe from a dynamical system point of view, there is only one attractor for these systems, but the point is that the invariant measure is clearly concentrated toward two well-separated domains of the phase space, which corresponds to these two polarities. So such phenomena are really very common in nature for turbulent flow. So there is a general question is, how would you define an attractor for very large dimensional systems like this one? So what our colleagues have done is to plot here all what they call the reversal path, the path to go from one part of the phase space to the other, from one attractor to the other. And they have put on top of each other all these transition paths, and you can see that these transition paths are somewhat predictable. The fluctuation here, when the transition occurs, are way smaller than the typical fluctuation for each of these attractors. And the dynamics has quite a specific shape. So it seems that in some cases, the transition from one attractor to the other often occurs through a predictable path. So all of these features are features that are common in equilibrium statistical mechanics and can be explained in many systems with large numbers of degrees of freedoms. Another example which is closer to the dynamics I will talk about later is what has been called transition between blocked and zonal states. I think it was an initial idea by Michael Gill, and the experiment has been done in the group of Harry Sweeney. What you can see here is a fastly rotating tank. So the dynamics is what is called the quasi-geostrophic type dynamics, which is dominated by the Coriolis force. And on these tanks, the experimentalists have put topography, which are these two gray areas here. And so the flow is affected by the presence of this topography. So this dynamics is described by a quasi-geostrophic dynamics. And what you can see is that on this plot, for instance, for the velocity measured at that point, this is the velocity as a function of time, you can see that there is seemingly two very different attractors which correspond to two different fluctuations for the systems. So it is found that these attractors have a large-scale organization of the flow, which are either this one of this type, or of that type. This type is called zonal flow. It means close to invariant by invariance by rotation around the axis, similar to and this one is called a block state because the flow is much more affected by the topography, and it is blocked in the sun, but it has no rotation. So the name has been coined by analogy with what happens in the atmosphere. So the kind of question is, how can we define the attractors? Can we predict their probability? Can we predict the transition pathway? And so on. So from a mathematical point of view, it's exactly what I just said. So from a mathematical point of view, we will use large deviation, for instance, for the dynamical case of the Freidling-Van Zyl theory. And basically the main question is, will large deviation result be valid for this kind of problems? So I want to stress what are large deviation and why they can be important for this kind of problems. So we look at the probability for an order parameter. Here the order parameter I will choose will be, for instance, the average, my velocity, my field will be the vorticity field, omega of x. And I will look at the probability that omega of x be equal to a value sigma at point x. So this gives me a probability that depends both on the space x and on the value for this field. So this is, as I have average over the dynamics or over all the possible states, this is a macroscopic description of my flow. So the typical question I will ask is, what will be the probability to observe such macro state for my flow? And I can expect that in some regime, the probability will take this form, c multiplied by exponential of minus some function f of p divided by epsilon. For instance, for equilibrium systems, f can be the free energy or the entropy, and epsilon is typically kBT over n. So if we are able to fulfill this program, which is to compute f, in a sense we solve the dynamics, because f from f we can deduce which is the most probable states, which are the typical fluctuation, and the phase transition are related also to the property of f when external parameters are changed. So I will not. So the point is that large deviation function f for non-equilibrium systems can be computed from the dynamics, as has been explained, for instance, by Yona Lasigno 2 days ago. So Yona Lasigno was basically fulfilling the same type of program in problems of particles interacting and transporting, for instance, a flow of energy. So here, for this kind of turbulence problem, I will not be able to fulfill completely the program, but I will give you partial answer. We will be able to do that for equilibrium, and we will do that in a less extent for some specific examples for non-equilibrium cases. So basically what we use is we try to compute this large deviation using instanton theory or just coarse graining for the equilibrium case for the microcanonical measure. So the key idea is that large deviation theory extends statistical mechanics tools to non-equilibrium systems. So this is a program which is a very difficult one, so we cannot expect to go far, for instance, towards climate application doing this program, but I think it is still a very important point. So I will begin by talking about the 2D Euler and the 2D Navier-Stokes equation, talking rapidly about equilibrium and non-equilibrium phase transition, and then I will speak about part of the program which consists in passing through stochastic averaging and jet formation, and I will do that in the examples of the quasi-geostrophic, the barotropic quasi-geostrophic dynamics. Most probably I will not have time to talk about the third part, which is about instanton and transition pathway, but I guess that Eric van den Eyden will speak about things which are very similar later on. So I begin with the 2D Euler equation, which is the simplest equation, which has this property to form this, which is turbulent and still form this large scale structure, which are stable. So here it is written for the vorticity. The vorticity is the curl of the velocity, and in 2D it is just a scalar. It is just aligned with the vector which is perpendicular to the plane. So I will define a stream function psi, and basically there is this relation them between omega and psi. So here when you look at the dynamics for omega, you see that it is transported by a velocity, and you compute the velocity from the vorticity, so it's a nonlinear transport. And this computation, for doing this computation, you have to invert the Laplacian, so basically it is a non-local thing. So it is a very simple dynamics. So as has been said by David Ruel this morning, it is a crucial thing that it is Hamiltonian. It is crucial things for different reasons. First, there are many invariants. There is the kinetic energy, and there is what is called the Casimir functionals, which are just the integral of s of omega for any function s, which are equivalent to the conservation of the vorticity distribution. So what we want to do is, and what has been done in the past by other people, I also worked on that, is to define for these Hamiltonian systems the equivalent of the microcanonical measure. So the microcanonical measure here will be a measure which will have the property of having all microstates equiprobable, but with the constraints that we will know the energy and we will know all the other invariants. So this is possible. I won't explain this in details. And basically, there is associated to this microcanonical measure large deviation result, which prove that the probability p to observe the value of omega equal to sigma at some point x will fulfill a large deviation principle as I was introducing before. And basically the large deviation rate function in this case will be just minus 1 over the volume of the domain multiplied by the integral over the domain of p log of p, where here we integrate both on space and on the value of sigma. So this is typically what we obtain when we have systems for which the correlation between the different points can be neglected. So it's very similar to, for instance, the H the formula by Boltzmann that comes into the H theorems. So the reason why the vorticity point can be understood as independent from one from the other here are related to a completely different reason. It is because there is a somewhat long-range interaction, and because each point feels the interaction of many other points. So this is the reason why such an entropy appears here to describe the probability of the macrostates. So then the point is that the probability concentrate close to supremum of this S with given constraints, which takes into account of the value of the invariance. And this predicts that the microcanonical measure is concentrated close to states which verifies such an equation where F depends on D, the vorticity distribution, and beta parametrically depends on E. So basically this equilibrium statistical mechanics predict that we will be concentrated close to steady states, just as we were seeing on Jupiter, for instance. So I just give you a phase diagram here. I won't comment it in detail. So this is energy. These are other parameters related to the conservation of the other invariants. So basically, I just want to stress that in a doubly periodic domain, we have two types of equilibrium states. Basically, equilibrium states for which the vorticity field as a dipole structure with a cyclone and anticyclone, and other equilibrium for which we have parallel flows. So now I will turn to dynamics, but I will change a bit the dynamics. I will now study the 2D stochastic Navier-Stokes equation. So the left-hand side is the same thing. It is the Euler equation, but I will add some non-inertial effects, for instance, friction, linear friction, viscous dissipation, and also the stochastic forces. Basically, F here will be a Gaussian field with which will be white in time and which will have some given correlation in space. So I will show you the dynamics through numerical simulation. So here I start, you see the vorticity field. So the green things is nothing, it is zero. And so I start from zero, from rest, and you can see the formation of vortices, basically at a scale initially that corresponds to the forcing scale, which is an intermediate scale here. So you have a very complex dynamics, which is really of a turbulent nature. It takes an extremely long time for the system to settle towards the typical state. And this second film shows you what happens when the system has settled. And here you can see clearly that actually the systems are settled close to a state which is genuinely turbulent. You have these filaments everywhere. You have a turbulence that actually transfer energy from this intermediate scale to the large scale, but still it is dominated by the dipole, which have this very specific position that were predicted by equilibrium statistical mechanics. So in a sense, but we have here a non-equilibrium problem, because these things do not satisfy detailed balance. There are fluxes and so on, but we are close to some equilibrium problems in some sense. So the 2D stochastic Navier-Stokes equation has also been studied a lot by many people from mathematical physics. Some of the names are here. There are many other names. For instance, I have added this one yesterday after the talk of yesterday. So basically, the kind of result is the existence of proof of the existence of a stationary measure, the limit of this measure when nu goes to zero, which is called the inertial limit. And basically, as was told yesterday, in this limit, almost all trajectories are solution of the 2D Euler equation. So there is, for instance, these books that has recently been published by Cooksin and Chirikian. So we want to try to go a bit further physically, I mean, to see where this invariant measure actually concentrate. I remember you that we have seen that there are two kinds of equilibrium states with different large-scale flow topology. So what we did is to empirically try to find where such line here, which is a phase transition between these two kinds of attractors, occurs. And so what we have actually tuned empirically the parameter to find that there are regimes for which we are actually able to see for this non-equilibrium problem the situation of first order transition between these two kinds of attractors. So you can see here as a function of time the order parameter, which is here just the Fourier component of the flow for the larger scale in this direction. So it is nearly zero for this parallel flow, and it has a non-zero value for this dipole. So what you see here are random switches between these dipoles and this parallel flow.
Can I ask what is happening? Why don't you get flows also in the other direction?
So in this case, the main control parameter is delta, which is the aspect ratio of the domains, and this choose basically between the flow in this direction or in the other direction. But as you will see later, if I have time, there are many other phase transitions for the same problems with different qualitative features. So we can try to attack these problems using large deviation for the dynamics, which is basically the Freiding-Wenzel formalism, and try to compute instantons. So we have done that basically numerically, but it was extremely difficult to obtain some analytical result. And we have understood recently that in order to obtain some analytical result, it was important to go through an intermediate step which is related to stochastic averaging. So this is what I will explain now. So we consider the, so I will change a bit the dynamics for two reasons. In order to be closer to geophysical application on one hand, and also in order for the attractors of the systems to be simpler. I mean, I will use what is called the barotropic quasi-geostrophic equation, which is relevant, for instance, probably to explain Jupiter structure. And it's the simplest model for this geostrophic turbulence. So it's exactly the same equation as before, except that the quantity that is advected is now Q, which is called the potential vorticity. And Q is omega, the vorticity, plus beta y. Beta y is a constant external field, where y is the coordinate between south and north. So this accounts for what is called the beta effect in the geophysics. And when I add this beta effect, then the statistical equilibria will be zonal flows, and this will make the problem much simpler. So I will study also in these problems what is called the inertial limit. So here I have written the same equation but non-dimensionalized, and when I non-dimensionalize the equation, I see that I have only three parameters left. Nu, which will be something like a Reynolds number, alpha, which will be something like a Reynolds number based on the large scale friction, and beta prime, which is a renormalization of my beta. So this number nu will be unimportant. It's related to small scale process, which is not what I am really interested in. And alpha, here I will choose to study the limit when alpha is very small. So physically it means basically that the time scale for the Hamiltonian dynamics, which will be much smaller than the time scale for this non-inertial effects, the time scale for putting the energy of the systems or for dissipating energy. So it is, there is sometimes the overdamped limit and the underdamped limit, so it is an underdamped limit. So the spin up or spin down time from a structure, 1 over alpha, will be much larger than the Hamiltonian time scale, which corresponds to my dynamical time scale. Yes?
So, am I to think of the forcing as coming at an intermediate scale and damping at a very large scale?
So exactly, I mean, damping of energy will be on the large scale, and damping and entropy will be on the small scale. And here actually we have a forcing which is at an intermediate scale, as you say, but it is not so important. The point is that the forcing will act on a gentle way compared to the large scale structure. So this is what is essential. We don't make much hypothesis on the spectrum of the forces of the following. So this is the kind of structure we get in the dynamics in this case. So it's a numerical simulation that has been done by Brian Farrell and Petros Ioannou. So you can see here what happens for the average. So it is the velocity u that depends only on one coordinate y as a function of time. So basically because the flow self-organizes into jets, which are zonal jets. So this is y, this is time, and you see that the flow settles close to an equilibrium, which has a velocity u here, which is flow alternatively to the left or to the right, and this is a function of the latitude y. So it is very similar to what happens in Jupiter, and what is extremely similar is the fact that there are very weak fluctuations close to this base flow. So this is basically what corresponds to this inertial limit. And the point is here that we will treat those weak fluctuation perturbatively. In order, so we will pass this to. Okay, so technically what we do is nothing else but stochastic averaging. So we do it in a way that is common for theoretical physicists. We write P of Q, the PDF for the potential vorticity field. So it's a P. So mathematicians do not like this because the Lebesgue measure does not exist. Here we are in a space of a function, but you could write exactly equivalently to that the adjoint equation for the observable. So, but we write formally directly the equation for P, and it gives us a Fokker-Planck equation. So the derivative of P over dt is some functional derivative of an operator where you recognize here the deterministic part of the dynamics, and you have here a second order term with respect to the functional derivative, which corresponds to the effect of the stochastic noise. So this is just formal. So the point is that we want to decompose the field into the slow flow, which is the zonal flow, and the fast variables, which corresponds to this eddy turbulence. So we make this decomposition just by averaging over the x variables. We just take the integral over x of the field Q, and so we obtain a field that depends only on y, and that we call the zonal part of the flow. So then we write that Q can be decomposed into this zonal part of the flow QZ plus some perturbation. And the point is that we will argue that the perturbation will go like the square root of alpha. Why? Because the forcing at any times will be of order of square root of alpha. So for this to be true, we will need this fluctuation to be dissipated rapidly. And it will have to be dissipated by this Hamiltonian part of the dynamics. So this is what is non-trivial. So let's take this as, for now, as an ansatz. Let's assume this, and I will argue afterwards that this ansatz is actually the good one. So then what we do is just stochastic reduction. So as is classically done in theoretical physics or in mathematics. And the point is to actually average out the effect of this turbulent part for the flow. So the details are quite technical, but there is no difficulty at a formal level. And so when we do that, we obtain the PDF R for the slow field, QZ. So R of QZ is now the PDF that describes only the zonal part of the flow. So the large scale, basically. And what we get is a new Fokker-Planck equation, which is described by the terms that were already present before, the new term here that account for the average effect of the fluctuation on the larger scale, and also a new diffusion coefficient. So I will briefly explain what it is. Actually, it is related to what is called a quasi-linear approximation in physics. So basically, at leading order, you should describe a fluctuation by a linearized equation close to a base flow, which will evolve very slowly. So at leading order, you can assume that this flow is constant, and you describe the fluctuation by a linearization close to this base flow. And then it gives you an Orstein-Lundbeck process, and you compute the effect of the fluctuation averaging over this Orstein-Lundbeck process on the large scale, and this is the meaning of this nonlinear term, this new nonlinear term that appears here. So these were already discussed before phenomenologically by other people, for instance Farrell and Ioannou. And this is a classical thing that we obtain, for instance, in the kinetic theory of plasma. So this is actually here on these curves, you can see two curves, two different curves that nearly superimposed, and they compare what is obtained by the turbulent flow and what is obtained by this dynamics. So these two curves here have been computed using only the deterministic part of the dynamics. So in what we obtain is something a bit different, because we also have a second order operator which describes the effect of the fluctuation and the effect of the noise. So there is a correction to what was obtained before. So this quasi-linear dynamics has been also studied in more complex models. So you can see here, for instance, work by Farid Aït-Shahalal with Tapio Schneider in Caltech. So they compare this quasi-linear approximation with DNS for a GCM model of using primitive equation for the Earth atmosphere. And you can see here that there is a very good comparison between this quasi-linear approximation and what is obtained in this GCM. So actually this is true only for this picture is for a fastly rotating Earth. It's an Earth that would rotate twice faster than the actual rotation rate for the Earth. And when you look at the same picture for the actual value for the Earth rotation rate, then the agreement is no more as convincing as this one. So it just means that the Earth dynamics is not in this quasi-linear regime, but in a sense it is not far from it. Okay, so what is the relation with this bistability I was discussing before? The relation is that actually for this range of parameters, there are two kinds of attractor. There is an attractor with 1, 2, 3, 4 jets, and there is another attractor with 1, 2, 3, 4, 5 jets. So we can, using this theory, predict the fact that there are two attractors, and so the idea is now to use the Freiding-Wenzel framework for this average equation in order to compute the transition probability between one of these attractors and the other. So I guess I have only a few minutes. So I want to just to show you some slightly different things we have done, but going extremely rapidly. So in statistical mechanics, there is what are called Langevin dynamics. So Langevin dynamics are stochastic dynamics for which you have detail balance. So the point is that here we can write Langevin dynamics for the quasi-geostrophic dynamics of the 2D Euler equation. So the key property is that F, the nonlinear part of the dynamics, verifies the Liouville theorems, or a generalization of the Liouville theorems. The fact that you will conserve the volume of the phase space, or generalization of this notion. So there are conserved quantity G, for what I was talking about before. And so if we choose to force the dynamics with a white noise such that the correlation function is exactly the same as the one that appears for the dissipation here, we will obtain exactly Langevin dynamics as in statistical physics. And then the point is that we can study the effects of time reversal and see that there is a duality at the level of the action. And when we assume this, we will be able actually to easily say that the transition probability of the direct process will be related to the transition probability of the dual process. So for instance, it means that if we want to go from one state to the other, it will be sufficient to look at the path from the second state to the first state. And this will allow to compute easily the transition path to go from one attractor to the other, and these transition paths in this case are called instanton. So we have worked on that, on this hypothesis, and we have basically shown that we are able to compute instanton in this framework. So we were, as I told you before, we have also computed numerically instantons in a non-equilibrium framework that time without making this hypothesis. And another type of project we have is to study to do numerical computation for these rare events. So we can do it through instantons or through least action, through minimization of the action, as I was telling before. But we also do it through multi-level splitting algorithm. And this is, for instance, an example for the Ginzburg-Landau transition, for which we can we show that using this algorithm we are able to find the most probable transition from one state to the other, which actually corresponds to instanton in this case. So I will stop now.
Thank you for a very interesting talk. Are there immediate questions or remarks? Yeah.
I just have a technical question.
Yes.
When you can you show me the slide with your variational problems of entropy?
You mean the equilibrium version?
Yeah. So just can you say a few words about how did you solve this problem? Did you use some deviations duality in this? This is a constraint.
This is a constraint variational problem,
Yeah.
which can be actually difficult to solve.
Yeah.
So I mean, there have been several algorithms which have been designed to solve them, or in some limits we are also able to solve them analytically. So probably you are interested by the numerical part.
No, I'm interested in analytical solution.
So in many cases, these problems are what we call leads to ensemble inequivalence, in the sense that the constrained variational problems, which correspond to microcanonical ensembles, are not equivalent to the unconstrained ones. So basically, there are more equilibria in the microcanonical ensemble than in the canonical one. So usually we have to take into account explicitly the constraints and to solve the constrained variational problem.
Yes?
So
the two solutions that we have shown are actually two solutions of the equation which Reichmann and Montgomery have discussed extensively in the 80s, the insane hyperbolic Poisson, which represents actually the stationary state of the relaxation problem for the Euler system. Now the question is the following. You have a lot of solutions. It's exact. It's natural logarithm of pressure of two Riemann theta functions. And both of them are found in this class. Transit from one to the other in normally should involve some, say, that some parameter is not fitting, but Euler equation is conformal invariant. It doesn't care. You can scale it up and down. So choosing the domain, the delta, 1.02, 1.04, which makes the jumps between the dipole and the jet, should not be exactly the reason for such a jump. No? What I want to say is the fact that you have a class of solutions, indefinite class of solutions. It's the exact solutions of thin hyperbolic Poisson. Reichmann, Montgomery, AT, progressing.
I'm not sure if I understand well the question, but
the question is, what is the factor effectively that allows the system to make this jump? Must be something different except the size of the box.
Listen, maybe this question can be discussed during tea time.
okay.
Since it seems it will take some time. You wanted to say something?
Yeah, short question. Why do you need the Rayleigh damping at all?
We don't need it. The same phenomena occur even if we don't have it. But from a physical point of view, it is essential. I mean that for a real geophysical flow, you have this flow of energy towards the large scale, and usually this flow of energy is damped by some processes. So usually it is damped by friction, which occurs in the boundary layers. For instance, in the experiments of Sweeney, there is a three-dimensional boundary layer on the top and on the bottom, and this is where this dissipation occurs.
Okay, well, thank the speaker again.